One of the more common distributions that we'll be working with moving forward is called the normal distribution, or normally distributed random variables. So these are the kind of classic bell curve that you may have seen before. So what we see from this bell is, so even though the heights are not probabilities with PDFs, because that's actually what we're looking at here, it's a density, not a probability directly, I at least have some idea of how likely it is that we'd be in the neighborhood of this, right? So certainly since it's higher here, it's more likely that I'd get a value near the peak of the bell curve than I would over at the tails of the bell curve on the side. So I've drawn the mean here, because this is our, I guess, first fact to know about the normal distribution, is that the mean is the peak of the bell curve. So what does this tell us? That means that we expect values to be clustered close together around the mean, with values further and further away to be less and less likely to occur. All right, so this is actually a pretty common situation. Now, we may not have things that are exactly normal bell curves, but they're still going to have this kind of bell shape. And so this is going to be a useful thing to talk about normal random variables. So the first thing I should talk about is this word normal. So this is what a normal vector is we take some curve, find the tangential plane, and then the perpendicular vector to that plane is the normal vector. For 99.9% of you, I expect that to mean basically nothing. My point is, this word normal has nothing to do with being common or usual like we think of the word normal, or that we should expect something to be normal, and if it's not this thing, it's abnormal. It's nothing to do with that. It has to do with this mathematical physics kind of idea of a perpendicular arrow away from a curved surface. It's for some very common applications in physics and mathematics. We want to use these normal vectors all the time, and it actually gives rise to something like this as you look closer to it in lots of applications. So drop the baggage of the word normal distribution. This is actually a fairly rare distribution to see out in the wild in terms of raw data. But it's still going to be really important for reasons that we'll absolutely get to at the end of this unit. But for now, just know that we shouldn't necessarily expect our data to look like this. Actually, it's going to be fairly rare. I can probably only fill up one hand's worth of things. I know newborn baby weights are pretty close to this. Heights for growth charts as children grow up tend to be normally distributed for the heights at a certain age. IQ scores. There's really not too many things. I would run out of possibilities pretty quickly with these normal data. So, what do we know about this thing that's actually uncommon but called normal? All right, so I've got some basic properties we should know about it. First, the normal distribution is symmetric about the mean. So, it is symmetric. That means, what does symmetric mean? It's that I can draw a line somewhere to where one side is a mirror image of the other side. And where I draw that line is the mean, right? So this, when I say it's symmetric about the mean, I'm saying that when we draw a line at the mean, one side is a mirror image of the other. Okay, so let's think about this. We know that the total area under this PDF curve is 1. And we know that when I split it right here, one side is a mirror image of the other. Mirror images are the same size. So can you guess where the median would be? Like where there's a 50% chance of being less than that value and a 50% chance of being more? Well, it's at exactly the same spot. So the median for this distribution, where there's a 50% chance of being less and 50% chance of being more, is exactly right here because it's symmetric. And I want to just throw out one more thing. This peak right here is the mode of a distribution, right? I would expect to get this peak value more often than any other value. So that's the mode. So the mean, median, and mode are all in exactly the same place for a normal distribution. Okay. So now the normal PDF for a random variable never touches the x-axis. Okay, so you may have heard of this in mathematics as something like an asymptote, okay, or an asymptotic relationship. So if I extend out my x-axis like all the way here as far as I can get with my camera at least, this is going to get closer and closer and closer, but it will never actually touch the x-axis. So, okay, we've possibly seen functions like this in mathematics before, but there's something relevant here. That means that no matter how far out I am away from these typical values, there's still going to be a tiny little bit of area. So there's still some probability that we are just massively away from the mean, which is, as I talk about, for example, I said that baby weights are normally distributed. If that were strictly speaking exactly true, then there's some probability of getting a negative 8-pound baby and some probability of getting like a 15-ton baby, right? We know that's not true, but as long as within the range of possibilities it looks like a perfect bell curve that matches up with this, we normally just call it normally distributed anyway. But there are situations, for example, this is what the kinetic energy of molecules at a certain temperature actually looks like, right? So this would be our temperature, and these would be the kinetic energy for it. There are some things that will have an insanely small, and some molecules will have an insanely huge kinetic energy. In the world of theoretical physics, whenever you hear of something like crazy possibilities, like the Hadron Collider will cause a supermassive black hole, like this is what we're really talking about, is that as soon as we get this kind of distribution of possibilities, there's some possibility of getting some insanely huge or tiny number from it. In reality, when we're not doing crazy particle physics, this doesn't really come up. But I just wanted to at least point out what that really means to say that the PDF never actually touches the x-axis. That means that somehow there's always some probability. I can never have a probability of 0 for a range of numbers with the normal distribution. Okay. And I say that normal PDF is uniquely identified by 2 parameters, the mean and the standard deviation. Okay, so that's just saying that all bell curves are essentially the same. I can just move them left or right by changing the mean, right? So if the mean were actually smaller, this whole thing would just be moved over. And they could have a different standard deviation. All right, so what was a standard deviation? A measure of spread. So that's how spread out the bell curve is, right? So its location is set by the mean, and its variability or spread is set by the standard deviation. Larger standard deviations will be a more stretched out curve. Smaller standard deviations will be a narrower curve. All right, I just want to talk about one last thing in this video. So let's just look at some examples, right? So, as we're looking at this, we should be able to identify which of these curves has the smallest mean and which of them has the smallest standard deviation, let's say. So I don't know what the mean and standard deviation of these curves is, but the peak of the curve for the blue, red, and orange here, these 3, where the peak is all at the same place, is 0. The peak is the mean. So the peak is at 0, so all 3 of these curves have a mean of 0. If I look at the green one, this one right here, we've got a peak at -2, right? So I don't want to look at the height. That tells me where the peak is, but I actually want to look at where the peak is on the x-axis here, which tells me it's -2. So this green one has the smallest mean because it's the furthest to the left. The peak is the furthest to the left. All right, now which one would have the smallest standard deviation? Well, the smallest standard deviation means it's the least spread out. For that, that's this tallest curve, this blue one here. That would be the narrowest curve and therefore the smallest standard deviation. And so this short, fat one right here, the kind of orangish curve here, would have the largest standard deviation. So as long as we can kind of identify that and say, okay, which one has the smallest mean, the largest mean, smallest standard deviation, or whatever. I can't tell you what the number is for the standard deviation, but I can at least tell you which ones have a smaller standard deviation, which ones have a bigger one. That's all I really want to get out of these pictures for a normal distribution.